So good afternoon, Todmorden. This is the beginning of everything. And as you can see from the subtitle, I'm going to be giving a brief description of the origin and the very early history of the universe. So where shall we start? Well, let's look out into the universe and see what's out there. This might look like a simulation, but treat it more like a 3D atlas. When we look out into the universe, we see lots of galaxies all at different distances from us. And when we map them out in terms of their position on the sky and their distance, we find this structure, which we're currently doing a fly through. Notice that the galaxies out there are not uniformly distributed throughout space. As we fly around this universe, our local bit of the universe, we find that there are some regions where there seem to be lots of galaxies and other regions where they seem to be a little more sparse. In some cases, the galaxies seem to be lined up in filaments. On the biggest scale, we seem to have a sort of filamentary structure, a web structure to the universe. And the question is, where did all this stuff come from? We know when we look out at the farthest reaches of the universe that we can see the so-called observable universe. We know it contains maybe 1 trillion or so galaxies. And each of those galaxies might have hundreds of billions of stars and who knows how many planets. We know it's all out there, but the question is, where did it all come from? We can take snapshots like this from the Hubble Space Telescope. And remember, in this particular shot, a long exposure of a very small patch of sky, there are perhaps 3 stars in this image. There's one at the top, one towards the middle, and one down at the bottom. So those 3 stars are inside our own galaxy. But everything else you can see here is a galaxy in its own right. So we're looking at thousands of galaxies in a tiny patch of sky. This is what tells us that within the observable universe, there must be many hundreds of billions, if not 1 trillion galaxies. But if all of that is out there, where did it all come from? So that's what I'm talking about, the creation of the universe. When did it happen? Well, our best estimate is that it happened 13.8 billion years ago. How long did it take to make the universe? Well, roughly speaking, it took about 3 minutes. And I'll explain why we come up with that particular number in due course. Where did it happen is a common question. But remember, we're talking about the creation of everything. And therefore, by definition, it happened everywhere. The creation of the universe did not occur at one point in space. It happened everywhere. Why did the universe evolve the way it did over the last 13.8 billion years? Well, because of the laws of physics. And I'm a physicist. This is why this interests me. And how do we know all this? Same answer, because of the laws of physics. So when we look at a game of chess, we can ask ourselves, what are the rules of the game that determine how a game of chess evolves? And I'm using this as an analogy to think about the universe. When we look out into the universe, can we figure out what are the rules of the game, which in the case of the universe is the laws of physics? Can we figure out what the laws of physics are by looking at the universe? Can we figure out what the rules of a game of chess are by looking at a picture like this? But of course, this picture doesn't tell us the whole story. We might look at this picture and come to the conclusion the various pieces on the board seem to come in 2 different colours. So maybe this is a game between 2 different people. But it's very difficult to tell what the rules are from this snapshot. And by the same argument, we can't simply look at a galaxy and figure out how that galaxy came to be. A snapshot doesn't give us all the information. It would be better for a game of chess if we could watch a game of chess being played out, move by move by move, and watch it from start to finish. That would give us an idea of what the rules of the game are. But we can't really do that by looking at a galaxy. Things are changing when we look at this galaxy, but they're changing so slowly it would take too long to figure out what the changes are. For instance, this galaxy might rotate once in maybe a few 100 million years. So for the next few years, we haven't got the patience to sit and watch it for as long as it would take to see things change. So what's the alternative if we think a snapshot is not good enough, and in a sense we can't watch a video of the universe evolving? The alternative would be, well, if we can't just watch one game, can we at least watch 1,000,000 games all taking place, 1,000,000 snapshots of 1,000,000 games of chess, all at different stages at the beginning or the middle or the end of the game? Maybe if we had lots of snapshots, we could get an idea of what's going on. So one picture of one galaxy isn't enough, but maybe lots of images of thousands of galaxies, or possibly even hundreds of thousands of galaxies, maybe that would give us an idea. Especially when we remember that in a snapshot like this, the Hubble Deep Field, we're looking at some galaxies that are quite close, but a lot of these galaxies are very remote, many billions of light years distant. And because of the finite speed of light, if these galaxies are very distant, it's taking a long time for the light to reach us, and so effectively we're looking back in time at some of these more distant galaxies. So although it's only a snapshot, we have got a snapshot in effect taken at different times as we look further and further back in time, as we're looking further and further into the distant universe. And of course, the Hubble Space Telescope is still in operation, but now we have another space telescope, the James Webb Space Telescope. This is taking images in the infrared, but it gives us similar information. It allows us to look back in time at the very distant galaxies, hopefully a little more distant and hence a little earlier in time than the Hubble Space Telescope. If we take enough of these snapshots, we might get an idea of what the rules of the game, what the laws of physics are that have determined how the universe has come to be. When we look a lot closer to home, this is gas and stars and dust within our own Milky Way galaxy. When we look on our doorstep, it all looks very complicated. It looks very complex. How can we possibly understand the rules of the game that have led to the structures that we see in this image? Well, one thing we have to remember is that just because something looks very complicated doesn't necessarily mean the rules of the game are very complex. For instance, if we take a mathematical set of coloured pixels, it's called the Mandelbrot set. It's a mathematical set that is generated from a mathematical equation. And this is just a tiny part of it. Just like a moment ago, we were looking at a very small part of the universe. Here we're looking at a very small part of the Mandelbrot set. And it doesn't really matter how much we zoom in, we will continue to see more and more and more detail. And some of these little motifs seem to repeat themselves, but if we look very closely, we realise they don't repeat absolutely, they just look similar to each other. In much the same way that 100 million stars in our galaxy might look, 100 billion stars in our galaxy might look very similar to each other, but they're not all identical. The same is true of this collection of coloured pixels, of which we're looking at only a tiny fraction. We're looking at 1,000,000 pixels here, but there are in principle an infinite number of pixels in the Mandelbrot set. So if this is infinitely complex, if we could zoom into any part of this and continue to see more and more and more detail that never repeats itself, how complex must the mathematical equation be that generates each and every pixel in the entire Mandelbrot set? Well, the mathematical equation that generates everything that you can see plus everything else in the Mandelbrot set is that equation there. I'm not going to explain it, I'm not going to say how it's applied, but that's basically all you need. It is an infinitely complicated set, but the rule that generates it is relatively straightforward. And that's what we're talking about with the universe. Complexity does not mean that something is incomprehensible. One of my favourite quotes from Einstein: the most incomprehensible thing about the world, or the universe if you prefer, is that it is comprehensible. In other words, we live in a very apparently complex system, complicated perhaps, but just because it looks complicated, just because it looks complex, does not mean that we can't understand the laws of physics that have generated it. So what's the flow of thought that helps us understand where the universe came from? Well, the observation made best part of 100 or so years ago was that galaxies are moving away from each other. They are all receding from our point of view. They seem to be receding away from us. We come to the conclusion that the universe is expanding on the largest of scales, not necessarily on a small local scale like the solar system or our own Milky Way, but when we look out into the distant universe, it appears that everything is receding from everything else. The universe is expanding. We have another set of observations that we can make, and that is we can do experiments on Earth to try and understand the nature of matter, the way things are put together, fundamental particles that make up atoms and molecules, and us, and the Earth and the Sun. And we can do experiments such as experiments at the Large Hadron Collider in CERN, where we can bang fundamental particles together effectively to see what happens. And we can smash atoms together and see what they're made of. We have to make some assumptions. And the assumptions we basically have to make are that the laws of physics in one place are the same as the laws of physics in another place. If the laws of physics in England were not the same as the laws of physics in Australia, we would have no chance of understanding the way things work. Similarly, we have to assume that the laws of physics don't change with time. The laws of physics now are the same as the laws of physics yesterday and are the same as the laws of physics will be tomorrow. If we do an experiment and get a result, but we find the laws of physics have changed tomorrow, again, we would have no chance of ever understanding the way the world works or the way the universe works. We have to assume that the laws of physics are immutable. We can't prove they are, but we can't make any progress if they aren't. So those are the basic assumptions. When we put all of that together, we come to the conclusion that the universe was created in a very hot, dense state 13.8 billion years ago, and ever since then it has been expanding and cooling. And the big question that we're trying to address is, where did all the matter that we see today come from? When we look out into the universe, we see all objects at a certain distance from us. We can't see beyond a certain limit. We call that the observable universe. The observable universe is currently about 100 billion light years in diameter. So we can see objects within that sphere. We can see all of these trillion galaxies, each of which contains hundreds of billions of stars. And we assume there's lots of planets out there as well. But where did all that stuff come from? How far back can we go? If we think the universe is 13.8 billion years old, how far back towards the beginning of everything can we go before we have to say we really don't understand what's going on? We really are not sure whether the laws of physics as we understand them at the moment still apply. Can we go back to the first year of the 13.8 billion year history of the universe? Yes, as far as we know, there's no problem. Can we go back to the first day? Yes. The first hour? Yes. The first minute? Yes. The first second? Yes. The first millisecond after the universe was created? Yes. The first microsecond? Yes. The first nanosecond? Yes. The first picosecond? No, not really. We can't go back beyond the first picosecond, the first trillionth of a second, and with all honesty say we know what happened. Before the first picosecond, we are on shaky ground. The reason there's a watershed at this 1 picosecond, this 1 trillionth of a second point after the universe was created, why that particular point, I'll explain that shortly. But everything after the first picosecond of creation we think we're on relatively solid ground. The main reason for that is because we can test any hypothesis, any theory we have can be tested from that point onwards. But prior to that point, there was so much energy rattling around in the universe that we're not sure how to test any of the ideas we would have. So for this fraction of a second onwards, we're okay. Before that, not too sure. So that was a rather long introduction to what I'm talking about. We're trying to establish how are we going to get a handle on how the universe began. The answer is we look at what the universe is like now and we try and determine the laws of physics, the rules of the game that tell us how it's changed from then to now. So in this talk, I'm going to start with a few basic ideas, basically one slide to make sure we all understand the basics, and then I'm going to ask what happened in the first fraction of a second, the first few seconds, the first few minutes after the creation of the universe. I'm then going to fast forward 380 or so thousand years, 377,000 years after the Big Bang. And then we're going to go very quickly to 13.8 billion years later, i.e. now. And of course, we're going to change gears to make sure we don't spend the rest of eternity dealing with the second by second evolution of the universe. So first, a few basic ideas. Some of these you'll be familiar with, some of these perhaps not. So firstly, we are made of atoms. I hope that's no surprise to any of you. An atom is a positively charged nucleus with negatively charged electrons buzzing around it. So you can, if you wish, take an atom and separate it into its component parts, a nucleus and electrons. To the best of our knowledge, an electron is a fundamental particle. You can't take an electron, cut it in half and have a look inside to see what it's made of. It's not made of anything. It is simply an electron. And as far as we can tell, it has no internal structure. A nucleus, however, is a so-called compound particle. It is made of something else. A nucleus is made up of protons and neutrons. And experiments over the last few decades, the last 100 years or so, have told us that protons and neutrons are also made up of other things. And we can take a proton and we determine that a proton is made of 3 fundamental particles, which go by the weird name of quarks. We're not going to turn this into a physics lesson and say, well, what is a quark and what is its properties? We're simply going to say that a proton is made of 3 quarks. And again, quarks are fundamental. As far as we can tell, you can't take a quark and cut it in half and look inside. A quark is not made of anything. It is just a quark. It is a particle with a funny name. Neutrons are also made of quarks. But the point I'm making in this particular slide is that we have a sort of a Russian doll here. We have atoms which are made of nuclei and electrons. A nucleus is made of protons and neutrons. A proton is made of quarks. And the amount of energy you need to split an atom into its component parts, or to split a nucleus into its component parts, or to split a proton into its component parts, that energy gets higher and higher and higher as you go to smaller and smaller and smaller structures. So there's an implicit energy scale here from low energy at the top to higher energy at the bottom. But to a physicist, low energy and high energy are sort of the same thing as low temperature and high temperature. Temperature is effectively just a way of measuring how much energy does each of the particles have in a particular system. And remember, the universe was made hot and is cooling down. So time runs from the bottom to the top because high energy is where the universe started and it's slowly cooling off as it expands, and so we have a cold universe at the top. So time starts at the bottom and moves to the top. What that means is the universe was made from the bottom up. If we start with a whole load of particles, we can't simply put particles together like making quarks into protons and making protons into nuclei and making nuclei into atoms. We can't do that as soon as the universe was born because it's simply too hot. There's so much energy around in the early universe. If you try and put quarks together into a proton, they have so much energy they would tear themselves apart. You have to wait until the universe has cooled off a bit before you can put quarks together to make protons. And you have to wait a little bit longer until the universe has cooled off even further before you can have protons and neutrons get together to make the nucleus of an atom. If you try and make a nucleus before the universe has cooled off, the protons and neutrons would have so much energy they would tear themselves apart. And similarly, you build up from the bottom up. You first make protons, then you make nuclei, then you make atoms, then you make molecules, then you make us. That's how the universe builds, from the bottom up. So let's start the story. Where do we start? Well, we can ask what happened at t equals 0, what happened at the instant of the birth of the universe. And from what I said earlier, you can possibly guess that the answer is we don't know. Science cannot provide a definitive answer of what happened at t equals 0. Some people have a hypothesis. Maybe it was a quantum fluctuation. Quantum theory tells us what happens to things on very small scales. And perhaps there was a fluctuation in which energy was borrowed from nothing. That sounds rather weird, that we can borrow something from nothing. But as far as we can tell, that doesn't violate any laws of physics that we understand. And if we can borrow energy, we can use energy to make matter, because E equals mc squared. Einstein told us that matter and energy have a sort of a symbiotic relationship. We can use energy to make matter, we can use matter to make energy. Borrowing energy from nothing sounds really weird. But yes, correct. Quantum mechanics is weird. That's the topic of a completely different talk, the weird world of the very, very small. So if we think it is possible to borrow energy from nothing, how does that explain the universe? How much can you actually borrow? Well, quantum mechanics tells us that the energy that you borrow multiplied by the time for which you borrow it has an upper limit. In other words, you can borrow a lot of energy for a short time, or vice versa, like a bank loan. If you take out a lot of money, you've got a lot of interest to pay, you try and pay it back quickly. If you only borrow a very small amount of money, then you're not so fussed about paying it back. You might take a long time to pay it back. So what matters is how much energy did the universe borrow in order to make everything that we can see? Well, again, we don't know, but it's very interesting to note that if you add up everything in the universe, if you look at all of the energy that we can see based on all of the matter, because remember, energy and matter are equivalent through E equals mc squared. If you work out all of the energy because of the existence of matter and all of the energy because of the existence of gravity, the total seems to be about 0. Because gravity is a negative energy and mass is a positive energy, and when you add them all up, the total might be 0. So perhaps the time period we are allowed to pay back the loan, perhaps that's infinite. This is very speculative. Some people think this is perhaps the answer. Some people think this is rubbish. There is great controversy about how we think t equals 0 actually gave us the universe that we see today. What happened next? Well, the universe expanded. It expanded from who knows what size, but after this ridiculously short length of time, 10 to the minus 35 seconds, the observable universe has expanded until it's about the size of a golf ball. By that I mean that everything that we currently see inside the observable universe, remember this sphere, 100 billion light years in diameter, everything that is currently observable to us used to be a lot closer together. The universe is expanding, everything used to be closer together. Everything that we now see in a sphere 100 billion light years in diameter used to be a few centimeters apart. That takes a little bit of imagination to imagine squeezing everything in the observable universe down to the size of a golf ball. Again, this is hypothetical. Just like a golf ball, the universe at this time was not perfectly smooth, but it had dimples in it. Let's take that phrase of dimples with a pinch of salt. What we mean is small variations in density and temperature. It wasn't perfectly uniform. So not dimples in the sense of dimples on the surface of the golf ball, but just small variations in density. And eventually, once the golf ball has expanded until it's much, 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 much bigger, those small variations in density would give rise to the formation of large-scale structures across the universe. The galaxies, the clusters of galaxies, the superclusters of galaxies that we currently see. So up till this point, everything has been hypothetical. But from this point onwards, we've got an idea of what's actually going on. So this is 1 picosecond, 10 to the minus 12 seconds after creation. The universe has expanded enormously. It's gone from the size of a golf ball to the size of, roughly speaking, the solar system. Of course, the solar system doesn't exist yet at this particular point, but just to give us an idea of how big we're talking. So it's expanded very quickly. In a tiny fraction of a second, it's gone from the size of a golf ball to the size of a solar system. The universe has expanded much, 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 much faster than the speed of light. The temperature has fallen to about 10 to the 15 Kelvin. And the energy of each of the constituents, whatever they are, if we've borrowed energy, we've been able to make lots of matter. Let's just assume that the matter we're making are quarks. It's probably a mixture of quarks and electrons and loads of other particles. But for convenience, let's just call it a quark soup. Lots of quark particles and other particles. The energy of each of the constituents in the quark soup is, roughly speaking, equal to the energy that we can create in the Large Hadron Collider. In other words, although it's a phenomenally high energy, it is something we can test. We can do experiments by smashing protons together, for instance, and generating the sorts of energies that we're talking about at this particular point after the Big Bang. And it's precisely for that reason that we can actually test our ideas in a particle accelerator that gives us the confidence to say we think we understand what's going on from this point onwards. From this point onwards, the universe is going to be cooler than this particular temperature of 10 to the 15 Kelvin. And it's because we can test our ideas that we have a reasonably good idea of how the universe evolved from this point onwards. We borrow energy and we make matter. Energy and matter are continually exchanging back and forth and back and forth. That's the nature of what Einstein summarized in E equals mc squared. Matter and antimatter are originally made in equal amounts. For every particle of matter, for every proton, for every electron, for every particle of matter, there is an equal and opposite particle, which is called antimatter. For instance, if an electron has a particular mass and a particular charge, an antimatter equivalent, an anti-electron, which is called a positron, has the same mass but the opposite electrical charge. As far as we can tell, every particle has an antiparticle equivalent. And back at this point in the universe, matter and antimatter were made in equal amounts. So if we take a certain amount of energy, I don't know how to represent energy other than to write it down as a big capital E. If we take a bit of energy, we can make matter and antimatter. We can make a quark and an antiquark, or an electron and an anti-electron. We probably won't be making a tangerine and an anti-tangerine, but the point is it doesn't matter, if you'll excuse the pun, what it is we're talking about. Energy converts into something and it's anti-equivalent. And those particles, the quark and the antiquark, or the electron and the anti-electron, will annihilate with each other and make energy. And this idea of energy goes to matter, which then goes back to energy. That energy will then make something else, not necessarily the same two particles again. It might make a different particle and its antiparticle. Again, probably not a hot dog and an anti-hot dog, but it doesn't matter which particular particle we're talking about. Energy converts into matter and antimatter. They annihilate to make energy, which makes matter and antimatter. And that process is going on back and forth very rapidly. Somehow, via a process that we do not really understand, matter gained a very small excess over antimatter. Naively, we might expect that we always generate the same amount of matter and antimatter, but somehow that symmetry was broken. What that means is, at this particular point in the early universe, we might make an awful lot of matter, but we might produce slightly less antimatter. Here I've shown it as something like a 10% excess of matter over antimatter. Now the excess was nowhere near that large. It wasn't 1 part in 10 that matter won over antimatter. It was more like 1 part in a billion. A very, very small excess. But when we start thinking about annihilation of matter and antimatter, and matter and antimatter, we can see that all of these matter and antimatter pairs on the left are going to annihilate with each other and make energy. Energy usually in the form of gamma rays, electromagnetic radiation. So the matter and antimatter is going to produce radiation, but what happens to this little bit of matter on the right-hand side? It can't pair up with any antimatter because of this imbalance. We're left with a little bit of matter. So we're left with a universe which is full of radiation, or light if you prefer, and a little bit of matter. But that matter is everything that we can see. All of us, you and me, and the Earth and the Sun and the solar system and the Milky Way galaxy and the other trillion galaxies that we can see in the observable universe are just that leftover bit, that 1 in a billion. That's why there are something like 1 billion photons of light for every particle of matter in the universe, because matter is only that little bit that was left over when all the light was generated. Let's move on to the first millisecond, the first 1/1000th of a second after creation. Matter and antimatter are continuing to pop into and out of existence. Now, protons and neutrons, remember those are not fundamental particles, they are made from quarks. And at this point, the universe has cooled down enough for quarks to start to get together. And I'm not going to go through the particle physics, but if we have a group of quarks which are labelled according to these particular cartoons here, let's not worry about what the U and the D mean, let's not worry about why they are labelled red, green and blue. The point is, when a particular collection of quarks get together in a bag, we call that particular bag of quarks a proton. And a different arrangement, a different collection of quarks, that's a bag that we would simply label as a neutron. So protons and neutrons are just labels we give to a particular collection of quarks, and a different collection of quarks gives rise to a different label to that particular particle. So protons and neutrons, because they're both made of essentially the same type of stuff, they are continually transforming into each other. Protons change into neutrons, neutrons change into protons, back and forth and back and forth. And that continues for the first few seconds after the Big Bang. At this point, 1 second after the Big Bang, the universe is now cooled to about 1 billion Kelvin. It's now essentially too cold for protons and neutrons to readily swap back and forth. They haven't got enough energy for the quarks to simply change their mind and to go from a proton to a neutron. At this point, protons, because they are a little lighter than neutrons, and they're lighter by about 0.1%. How do we know? Because we can measure them in the laboratory today. We know that protons are a little lighter, and we have no reason to believe that the protons and neutrons in the early universe are in any way different from the protons and neutrons that we see today. So if protons are a little bit lighter than neutrons, and we can no longer swap backwards and forwards, we find that protons outnumber neutrons. They are not made in equal numbers because they are not the same mass. Why should that make a difference? Well, because nature always favours the lower energy. Given a choice, nature will take the easy way out. In other words, the lower energy, which is the same thing as the lower mass. Protons have got a lower mass, so they're easier to make. So nature chooses to make more of them. We end up, after 1 second, with the ratio of protons to neutrons, indicated here by the red dots and the blue dots. We end up with a ratio of 75 to 75. And just for illustration, I've chosen to pick out 16 representative objects, of which 3/4 of them are red and 1/4 are blue. So 12 to 4. What happens if we move forward a little way? If we move forward to the first couple of minutes or so, the first 2 or 3 minutes, because neutrons are unstable, some of them change into protons. How do we know that neutrons are unstable? Because we can do experiments today in the laboratory and we find neutrons do indeed change into protons. And so the ratio of protons to neutrons changes, and instead of being 12 to 4, it's now 14 to 2. 2 of those blue dots have now changed to red dots because 2 of the neutrons have changed into protons. So after 3 minutes or so, we have a certain ratio between protons and neutrons. And the universe, after 3 minutes, has cooled to about 100 million Kelvin. That means that nuclei can now start to form. In other words, protons can start to get together with neutrons. They want to do that because protons and neutrons, when they get together, can make a very stable structure. In other words, the universe wants to make this. 2 protons and 2 neutrons is a particular structure which is extremely stable. It's called an alpha particle, also called the nucleus of a helium atom. But of course, we only have a certain number of neutrons to go round. All of the protons would like to do this, but out of the 16 particles that we've shown here, 2 of the protons can get hitched with 2 of the neutrons to make this very stable nucleus of helium, but that leaves us with 12 bachelors. It leaves us with 12 protons that don't have a neutron to pair up with, and so we're left with 12 bachelor protons, otherwise known as the nuclei of hydrogen atoms, and we have 1 particle, which is 2 protons and 2 neutrons, which is either an alpha particle or you can label it as the nucleus of helium atom. And after 3 minutes, that's it. Once that has happened, you can no longer change the balance between protons and neutrons. Once the neutrons are in the nucleus of helium, they will no longer change. So after 3 minutes, the relative abundance of hydrogen and helium has been determined. And the Big Bang Theory makes this prediction that if the Big Bang Theory is correct, then after 3 minutes, you will end up with a universe which is 3/4 hydrogen and 1/4 helium. When we look out into the universe and we look at what gas is out there, bear in mind that stars change hydrogen into helium, but the universe is only 13.8 billion years. It hasn't had time to change much of that hydrogen. When we look at how much hydrogen is out there and how much helium is out there, we find the ratio of those 2 gases is 3/4 hydrogen, 1/4 helium, just as the Big Bang Theory would predict. That is one of the reasons that we think the Big Bang Theory is correct. It gives us the right relative abundance of hydrogen and helium. Very small amounts of other elements, but I'm not going to talk about those. After those 3 minutes, nothing much happens. For the next 1/3 of a million years, 377,000 years it takes before anything interesting happens next. During that 1/3 of a million years, the universe will continue to expand and it will continue to cool. Eventually, the universe cools to the point where it's at approximately 3000 Kelvin. And that is important. Why 3000 Kelvin? Because at this temperature, a nucleus can hang on to some electrons, and so atoms can exist for the first time. Prior to this, the universe was too hot, and you try and get electrons to go around a nucleus, the universe is too hot, the atoms will ionize and the electrons will be stripped off. But at this point, when the universe is 3000 Kelvin or colder, at that point nuclei can hang on to these electrons, and the universe changes from an ionized collection of atoms called a plasma to a collection of neutral atoms, atoms that do not have any net charge. At this point, for the first time, the universe becomes transparent to light. Up to this point, the universe was a plasma and was completely opaque. Any attempt at light to travel through the universe kept getting scattered by all of these ionized atoms, or nuclei or electrons. So up to this point, the light was effectively trapped in an opaque medium. But from this point onwards, the universe becomes transparent and that light is released. Now, the light originally, when you heat something up to 3000 Kelvin, it'll look white hot. It'll emit a huge amount of visible light and some ultraviolet light as well. Ultraviolet light and visible light has a wavelength of order microns, millionths of a meter. And although that light was released at the time, since then the universe has been continually expanding and stretching the wavelength of this light that was released at this particular point. And the universe is now 1,000 times larger than it was when this happened. And so the light that was originally a micron or so in wavelength has now been stretched until it's millimeters in wavelength. And what happens when you take light and stretch it until its wavelength is a millimeter? You find that the light is no longer visible light, it's now microwave light or microwave radiation. So light that was originally visible, the afterglow of the Big Bang, has now been stretched to the point where it is what we call the cosmic microwave background, the afterglow of the Big Bang. The observational evidence for the microwave background existing is a second strand that tells us the Big Bang theory is probably correct, because it explains why the cosmic microwave background exists. It's essentially the same in all directions, but there is a little bit of variation. You can see that when we expand the hot spots and dark spots, these are only tiny variations in temperature. They are only a few parts in a million hotter here or colder there, as you can see from the red dots or the blue dots. Only small variations, but there are definitely visible variations in the cosmic microwave background. And they are the result of the dimples that we saw in the golf ball right at the beginning of the Big Bang. Small variations in temperature when the universe was very small have now imprinted themselves on the cosmic microwave background, and we see those small variations. And these variations ultimately gave rise to the structures that we see in the universe. The small variations, as I've just said, are the result of the dimple. So in a sense, if we study those small variations in the cosmic microwave background, we are in a very real sense looking back at the very early universe. And that's why there's so much interest in studying as accurately as possible, in as much detail as possible, what the variations in the microwave background are. It gives us an insight into the very early universe. We can run simulations to basically ask the question, well, how do we go from the very early universe where there's small variations, how do we go from there to the universe that we see today? And simulations give us the answer. If we take a large chunk of the universe, not the entire universe, but a large chunk of it, and put in some small variations in density and temperature, so we haven't got a completely uniform volume full of hydrogen and a bit of helium. Let's fill it with gas, but put in a small variation of density and temperature, and then let gravity do its stuff. What does the simulation tell us we can expect to see? If we run the simulation, we see that gravity makes the dense parts denser and the less dense parts less dense. Here, the white regions are the more dense regions. We see that we're starting to get not a uniform distribution of white dots. We're not seeing a uniform distribution of galaxies. We're seeing galaxies pockmarking the universe. We're seeing clumps of galaxies. We're seeing clusters of galaxies. We're seeing filaments where galaxies seem to be lined up in lines. We're seeing a web-like structure where some regions appear to be almost empty of galaxies, like on the right here at the top, and some regions appear to be very densely packed with galaxies. The simulations tell us that's what we would expect if we start with a universe which is not quite uniform and we allow gravity to spend a few billion years pulling things together. We end up with a cosmic web which looks not dissimilar to, remember that 3D fly-through that I started with? This is pretty much what galaxies look like on the largest scales. They are not uniformly distributed. They seem to have a sort of web-like structure. If we were to map out the neighborhood of the Milky Way galaxy, this is our immediate neighborhood. There's the Milky Way roughly in the middle, the Andromeda galaxy in the bottom right, and we have a few smaller galaxies, some dwarf galaxies that are effectively satellites of the Milky Way. If we were to expand this scale to look a little bit further out, then our so-called local group, which is what we saw in the previous slide, our local group is in the center there, and if we look further afield, we see there are clusters of galaxies. Again, we see that it's not uniform everywhere. Some regions appear to be quite sparsely populated with galaxies. Other regions, like the Virgo cluster, the Fornax cluster, etc., appear to be quite densely packed with galaxies. And notice that these galaxy clusters seem to form in roughly straight line. There seems to be a filament here joining lots of clusters together. If we do that again and look at a larger scale, so we zoom out still further, then the Virgo supercluster is sitting there in the center, near the center, and we see this web-like structure when we plot out the neighboring galaxies in the vicinity of our own Milky Way. Not only do we see this filamentary structure, but we see regions which appear to be almost empty, like this Brouet's void on the right-hand side there. This, remember, is all the result of the fact that the universe did not start perfectly uniformly, but had small variations, small dimples in the cosmic golf ball, which ultimately gravity grabbed a hold of to produce the cosmic web of filaments and voids. So what about the next 13.8 billion years? Well, now that we have hydrogen atoms, the Big Bang Theory tells us where the hydrogen comes from, and that is the fuel for all of the stars that we see in the observable universe. Now that we understand where hydrogens come from, we can understand the existence of galaxies and stars within the galaxies, and we can understand planets and trees and mountains and snowflakes and rainbows and cats and okay, maybe not cats. I'm not sure we'll ever understand cats, but basically once we have got a handle on where the hydrogen comes from, then we have a chance of understanding everything else. Yeah, sure, there are still some details of cosmic evolution that we've yet to work out, but as long as we understand that we start with a lot of hydrogen, then most of the pieces of the jigsaw fall into place. Let's have a look at the timeline, just to remind ourselves as a sort of visual summary. This is a ridiculous timeline where it's fractions of a second on the left and billions of years on the right. So that's where we are, 13.8 billion years after the Big Bang. Right on the extreme left is this hypothetical cosmic golf ball that we assume must have existed in order to give rise to the structures that we now see. Energy was borrowed from nothing, and that energy was used to make matter. Lots of quarks and electrons and other particles. Let's just call it a quark soup. After a little while, those quarks got together into what we call protons and neutrons. A bag of 3 quarks can be labelled a proton or a neutron depending on which quarks are present. After a few minutes, those protons and neutrons get together to make atomic nuclei. Because there are more protons than neutrons, because they're lighter, we end up with more hydrogen than helium. After 3 minutes, that has been fixed. Nothing much happens for the next third of a million years until electrons come onto the scene and start to hook up with the nuclei. They've always been there, but up till now it's been too hot for them to hook up with the nuclei. Now we have atoms. Now we have a transparent universe. The light is released and we see that light as the cosmic microwave background. We then have a rather uncertain time period that we call the Dark Ages before we have stars and galaxies. We know that stars and galaxies have existed for many billions of years, but what we're not too sure about is exactly what happened in this early stage. After the cosmic microwave background was released as light, how long did it take until the first stars and the first galaxies were born? That is precisely why the James Webb Space Telescope is looking back in time as far as it can to try and understand the formation of the first stars and the first galaxies, so we can start to understand this period of the Dark Ages before the first stars came along. I've said if we start with hydrogen, we understand a lot, but unfortunately not everything. Our jigsaw is still not complete. There are some fairly fundamental questions that we still have not answered. Why did matter win over antimatter? As far as we can tell, it must have done, because we are here and essentially everything we see in the observable universe appears to be matter dominated. Only tiny amounts of antimatter are left. What caused the asymmetry in the first place? We can measure that asymmetry by doing particle physics experiments, but we don't understand why. What is dark matter? Dark matter appears to exist and gives a gravitational influence which makes the galaxies rotate at, I've said the wrong speed. It makes them rotate at a speed which is not what we would expect by looking at all the matter we can see. When we add up all of the matter of all the stars and all the gas and all the dust, it looks like objects are moving faster than we would expect, indicating there's more mass present in a galaxy, producing higher gravitational fields to explain why things are moving as fast as they are. And we really don't understand dark energy either. Something is causing the universe to accelerate its expansion, if we've got our theory right. So the universe has been expanding for 13.8 billion years, and we thought it might be slowing down, but the latest data seems to indicate the universe is actually accelerating its expansion. And again, we don't understand why, and we've simply given it the label dark energy, pretending that that's an explanation. But it isn't an explanation, it simply is a statement of our ignorance. So, this talk was titled The Beginning of Everything, but I tried to make it clear that when we say everything, I was talking about what's out there. All of the galaxies that we can see, all the stars that we can see, all the planets, all the stars, all the galaxies, all the gas, all the dust. Everything that we see is what I was talking about. But everything that we can see apparently only accounts for about 4% of the total that's out there. The other 96% is this enigmatic dark matter and dark energy. And that still remains a bit of a mystery. But as they say, that's another story. Thank you for listening.
Wow, gosh. If you'd like to stop your screen share, Steve, that would be